The turbine of a gas turbine engine can be likened roughly to an axial flow compressor working in reverse. The first part of the turbine is a stator section, which is called a nozzle guide vane. The nozzle guide vane directs the air axially onto the blades of a rotor section. The turbine extracts the different forms of energy from the hot gases that flow through it, and converts that energy into mechanical energy, which it uses to drive the compressor and gearboxes connected to it. Gearboxes can be used to operate accessories or, in the case of engines that do not use predominantly jet propulsion to generate their thrust, to power propellers or rotors. The energy available in the gas stream flowing through the turbine takes several forms. There is the heat energy, the potential or pressure energy, and finally the kinetic energy, which comes from the velocity of the gas stream. The conversion of all these forms of energy into mechanical energy means that their values will be reduced as the gas stream passes through the turbine. Nevertheless, having said that, the velocity of the gas in the combustion chamber is lower than the eventual velocity of the gas when it reaches the exhaust unit. During normal operation of the engine, the rotational speed of the turbine may be such that the blade tips travel at a rate in excess of 1,500 feet per second. At the same time, the temperature of the gases driving the turbine can, in a modern engine, reach as high as 1,700 degrees Celsius. The speed of these gases is as high as 2,500 feet per second. That is close to the speed of sound at these temperatures. These factors mean that a small turbine blade, weighing only 2 ounces when stationary, can, while it's rotating at its maximum speed, exert a load along its length which exceeds 2 tons. This tensile loading, coupled with the tremendous heat, causes a phenomenon called creep, which is the stretching of the metal of the blade beyond its ability to reform back to its original length. Whatever materials have been used to produce the turbine, and however carefully the temperature and the rotational speed limits of the engine have been observed, creep will, nevertheless, cause the length of the blade to increase over a period of time and engine operating cycles. A blade will have a finite life before failure occurs. The turbine blades of early gas turbine engines were manufactured from high-temperature steel. Use of this material imposed a stringent limit upon the temperature at the rear of the engine, and because the gas turbine engine is a heat engine, it follows that the power output of such engines was limited as a consequence. The next advance in turbine technology was the use of nickel-based alloys. These were subsequently superseded by superalloys. Superalloys are a complex mixture of many different metals: chromium, cobalt, nickel, titanium, tungsten, carbon, etc. Blades manufactured from superalloys have a maximum temperature limit of approximately 1100 degrees Celsius, or, if the blades are cooled internally, 1425 degrees Celsius. Traditional metal manufacturing processes produce a crystal lattice or grain in the material. The boundaries of the crystals create a weakness in the structure, and are usually the starting point of any failure. Some turbine blades are manufactured by the process of powdered metallurgy, in which powdered superalloys are hot-pressed into a solid state. The blades thus produced have long, slender crystals, and are very creep-resistant. However, in the search for even stronger materials, a procedure called single crystal casting is now being used in the most advanced engines. This type of blade has been directionally solidified via a spiral selector, which permits only one crystal to grow in the blade. This process virtually eliminates corrosion and creates an extremely creep-resistant blade. Ceramic materials are also being used in the production of turbine blades. Originally, the ceramic was applied as a plasma spray, the coating giving very good protection against a corrosive condition caused by a reaction between the base metals of the blade, the sodium in the air, and the sulfur in the fuel. We have seen earlier, in the lesson on compressors, that the compressor added energy to the gas stream by increasing its pressure. That energy is extracted in the turbine by reducing the pressure of the gases flowing through it. This drop in the amount of the pressure energy occurs both as it's converted to kinetic energy, or a higher velocity in the nozzle guide vanes, and also as it's converted into mechanical energy in the turbine blades, as is illustrated in this graph. We've already seen that the turbine stage consists of two elements, one row of stationary nozzle guide vanes and one row of rotating turbine blades. The complete turbine assembly comprises one or more turbine stages on one shaft, which, if coupled to a compressor, forms a spool. This picture shows a cross-section of a single-shaft three-stage turbine, similar to that used on the Rolls-Royce Dart turboprop engine. There are certain features shown in this diagram which are worthy of special note. The divergent gas flow annulus affords longer and longer blades to be fitted to each turbine stage moving backwards in the engine. This enables the velocity of the gas stream to be controlled as the gas expands into the larger volume available to it. The blade shroud shown here is fitted in an attempt to minimize losses due to leakage across the turbine blade tips. It also reduces the vibration of the blades. The clearance between the blade tips and the turbine casing varies because of the different rates of expansion and contraction of the materials involved. In some engines, an abradable lining is used in the turbine casing area to reduce gas leakage through this clearance between the blade tips and the turbine. But active clearance control can be more effective at maintaining minimum tip clearance throughout the flight cycle. This picture shows its use on an American engine. When a turbine is coupled to a compressor to form a spool, for peak efficiency and to ensure that stall and surge do not occur in the compressor, the spool must rotate at a speed which conforms to the requirements of the compressor. We saw in the lesson on compressors that the optimum speed of the spool is that of its design point. A free turbine, sometimes called a free power turbine, is a turbine which is not connected to the compressor. It's connected only either to the propeller or to the rotor reduction gearbox. The fact that it's not connected to a compressor allows a free power turbine to seek its own optimum design speed, rather than that of a compressor. The free power turbine has further advantages. The propeller of a free power turbine engine can be held at low RPM during taxiing, thereby reducing noise pollution and wear on the brakes. A free power turbine engine requires less starting torque than does an engine where the turbines and compressors are coupled together. A rotor parking brake can be fitted to an engine with a free power turbine. This eliminates the dangers inherent in having propellers rotating in windy conditions on the ground. The power output of a turbine can be increased by increasing its diameter. But this would have two detrimental effects. Firstly, it would increase the drag factor by requiring that the engine be designed to have a large diameter. And secondly, that greater stresses would be imposed because of the greater centrifugal forces created. A more effective method is illustrated in this picture, where an increase in the number of stages which comprise the turbine allows an increase in power output with a reduction in turbine diameter. It's a fact that the efficiency of a turbine blade increases as its rotational speed increases. The losses reduce in proportion to the square of the mean blade speed. Unfortunately, the stresses on the blade increase in proportion to the square of the blade speed. It would seem then that the engine designer is locked into a vicious circle, where any attempt to increase engine efficiency by increasing turbine speed would require stronger blades. This would mean making them heavier, which would create greater stresses on them, and so on ad nauseum. All is not lost, however. The advent of the high-ratio bypass engine, with its much greater propulsive efficiency, means that for a given thrust it can have a smaller diameter turbine. This, to some extent, circumvents the vicious circle problems mentioned previously. The high bypass ratio type of engine shown here consists of 3 spools. Firstly, we have the high-pressure spool, driven by the high-pressure turbine, which rotates the high-pressure spool at relatively high speeds. Then, to the rear of the high-pressure turbine is the intermediate pressure, or IP turbine, driving the intermediate pressure compressor through a shaft which spins inside that of the high-pressure turbine. Finally, the rearmost turbine is the low-pressure, or LP turbine. It drives the low-pressure compressor, more commonly called the fan, through a shaft which runs inside the high-pressure and the intermediate pressure shafts. Nozzle guide vanes are of aerofoil shape. The space between 2 nozzle guide vanes forms a convergent duct. Within this convergent duct, some of the potential or pressure energy in the gas stream is converted to kinetic or velocity energy. The turbine blades themselves can be impulse type, which is similar in action to a water wheel, reaction type. These blades rotate as a reaction to the lift they create as the gas stream flows over them, or a mixture of the 2 types, which is called impulse reaction. This picture shows 3 end-on views of the combination impulse reaction blade. It illustrates how the shape of the blade changes from its base to its tip. The shape change is accomplished by the blade having a greater stagger angle at its tip than at its base. This gives the blade a twist, which ensures that the gas flow does equal work along the length of the blade, and also enables the gas flow to enter the exhaust system with a uniform axial velocity. Normally, gas turbine engines do not use either the pure impulse or the pure reaction type of blades. The proportion of each type of blade utilized is dependent upon the design requirements of the engine. In general, the combination impulse reaction is more commonly used. Impulse type turbine blades are used in air starter motors. It's very rare to find pure reaction blades being used. When they are, the nozzle guide vanes are designed to divert the gas flow direction without altering the pressure of the gas. The considerable stress imposed upon the turbine blade and the turbine disc when the engine is rotating at working speed makes the method of fixing the blade to the disc extremely important. The fir tree fixing is the most commonly used system on modern engines. The serrations which form the fir tree are very accurately machined to ensure that the enormous centrifugal load is shared equally between them. The blade is free in the serrations while the engine is not rotating, but during operation the centrifugal force imposed holds it firmly in place. The turbine is a very efficient mechanical device. Nevertheless, it does suffer losses during its operation. On average, the energy loss in the turbine is about 8%. This 8% is comprised of approximately 3.5% from aerodynamic losses in the turbine blades and 1.5% aerodynamic losses in the nozzle guide vanes. The rest is divided fairly equally between gas leakage over the blade tips and exhaust system losses. The maximum temperature that the turbine assembly can withstand limits the thrust or power available. Exceeding the maximum turbine temperature will cause irreparable damage to the engine, Therefore, it's imperative that the turbine temperature is monitored closely. The temperature of the turbine is measured by thermocouples, which are placed in the gas flow somewhere in the turbine assembly, typically after the high or low pressure turbine. The temperature measured at this point would be termed the exhaust gas temperature, or EGT. Other terms that are used to represent the value of the gas temperature around the turbine zone are turbine inlet temperature, or TIT, turbine gas temperature, or TGT, jet pipe temperature, or JPT. The jet pipe temperature is so named because of the position of the thermocouples. They are actually placed behind the turbine in the jet pipe itself. In some modern engines, the thermocouple probes are fitted inside selected fixed nozzle guide vanes to enable temperature to be sensed without the probe being battered by the high-velocity gas flow. As the engine is accelerated to produce more thrust or more shaft horsepower, the exhaust gas temperature will increase in proportion with the extra fuel flow, and vice versa. That completes the lesson on turbines.